Partial fractions. Resolving a rational expression into partial fractions involves having several constants as numerators, and then it's a case of once you multiply it out into identity, which technique can you use to find the values of those? There are two. There's numerical substitutions and equating coefficients. Take this one for instance. Well, the first thing will have to be to factorise that denominator. So the numerator can stay the same. And the denominator, you can either use synthetic division or you can be aware of your difference of cubes. That's x minus 1 times, and then it's just all the positives of the remainders, which means that in terms of partial fractions, that being irreducible, a negative discriminant, would have something over a minus 1 plus being an irreducible quadratic, I'll have to have a linear term on top of that one. Then multiplying throughout by those denominators, I would arrive at this. I'd have a times that quadratic plus bx plus c times that linear term should equal 6x squared plus 5x plus 1. Now, that's not an equation, that's an identity. That's true for all values of x. So that I could choose any value of x that would be convenient to work out a, b and c, or I could compare them term by term. Since it's an identity, all the x squared terms should come to 6 and all the x terms should come to 5 and so on. But first of all, numerical substitutions, and there's an obvious one, but I'll do it completely by numerical substitutions. So first of all, the obvious one would be this, let x equal 1. Because that's going to knock out that term completely and just leave you with this one. So it'll be a times 1 plus 1 plus 1, which is 3, equals, and it's quite easy with 1, because that's just going to be 6 plus 5 plus 1, which means I've got 3a equals 12, so a is going to equal 4. So that'd be the first part. That was quite easy. Now the next part, I can't really knock out these other parts here, so what I'll do instead is I'll just pick other convenient numbers. The simplest number I can think of is 0 in terms of calculations. So if x was 0, I would have a times 1. The 0 would knock out b, very handy, times, and that would just be negative 1, and the other side would just come to 1. So that's a nice simple calculation, and I know what a is. A is 4, so that simply says 4 minus c is 1, so c is going to be 3. That was quick and easy. And then the only other easy one I've got would be negative 1. So if x was negative 1, just have to be slightly more careful with this, because that's going to be 1 minus 1 plus 1, so I'll just be 1, plus, and that will be negative b plus c, and that will be negative 2, but of course I know what these numbers are anyway, equals, and then on this side that's going to be positive, so it's going to be 6, I'll put it down, 6 minus the 5 plus 1. Just need to tidy this bit up. I know that a is 4, and that's going to be plus 2b and minus 2c, so minus 2 3s is minus 6, it's going to equal in this case 2, so you've got 2b is equal to, and that's what, a negative 2, so that's going to make that a 4, so b is equal to 2. So the expression is going to be a 4 over x minus 1 plus 2x plus 3 over x squared plus x plus 1. Right, that was using numerical substitutions, and that was fairly quick. Next bit. Equating coefficients. Now if I was to do it wholly by equating coefficients, I would simply do this. I would just go through them all. There are three constants, so I'll need to use all three of the parts. So x squared terms, I've got an ax squared and a bx times x and a b. So I've got a plus b should equal 6. X terms, I've got an a lot of x there, I've got minus a b and plus a c for the x's, minus a b plus a c, and that should come to 5. And then the constant, I've got an a, b's not going to produce any constants, and a minus c should give me that 1 at the end. See, this is quicker because it doesn't have all these numerical calculations, but I do end up with simultaneous equations to solve, and it just depends on the nature of them, how quick that is. Normally you might do something like, say for instance, well, I've got a and c. If I had another one that said a and c, I could do a pair of simultaneous equations, and so you could say take these two together because the b's would cancel out. If I take 1 and 2 together, I've got 2a plus c equals 11, 2a knock out plus the c equals 11, and then I could put number 3 into that, a minus c equals 1, add them up, 3a equals 12, so once again a equals 4, then the rest just batter out straight after that, because once I know that a is 4, 4 minus c, I can put that straight away there, 4 minus c equals 1, so c equals 3, and 4 plus b is 6, so b equals 2. But sometimes there's quicker little bits if you search within it, because if I took all 3 of those equations together, notice plus b plus c minus c, but that depends on any particular one. If I add all 3 together, then I would have this. I would have 3a equals 12, so a equals 4 straight away, and then just pump them back in and you get the other 2. So that would be it by equating coefficients. Less calculations I think, but then more in the way of simultaneous equations. But the best way of all would be to have a compromise between the two of them. Use numerical substitutions for as long as they last with numerical simplicity in that they knock out terms, and then revert to simultaneous equations by equating coefficients. Although sometimes the equating the coefficients will just give you it straight away. So the suggested method for this one would be, I think first of all I'd start with let x equals 1, because immediately that's going to knock that out, and so same as before I've got 3a equals, and if that's equal to 1 that's going to be 12, so I've got that a equals 4. And then rather than reverting to numerical calculations for both sides, I would then switch to equating coefficients. Choosing convenient ones though, because sometimes not all 3 are involved. So if I took the x squared terms, there's only an a and a b producing x squareds. A plus b should equal 6. So straight away, since a is 4, I can say b equals 2. And then instead of going for the x's, because all 3 are involved in x's, if I go for the constant, b's not involved. So if I go for the constant term, then that says a minus c equals 1. But I know a is 4, so that means straight away c is 3. And I would maintain that that would be the neatest way to go through that. Using numerical substitutions when they're convenient, and then going to equating coefficients. Right. Here's one you would expect you wouldn't need to resort to equating coefficients at all, because you've got 3 nice clean little linear denominators. Well, that would just break into a over x plus 1, b over x minus 1, plus c over 2x minus 1. So that multiplying it out, you would have a times x minus 1, 2x minus 1, plus b times what it doesn't have, x plus 1, 2x minus 1, plus c times x plus 1, x minus 1 equals that thing there, 6x squared. Ooh, 7x minus 1. Right, and then you would say fairly obvious on that one, I've just got to put in knockout values. So I'm going to let x equals, I'll just pick one of them first of all, like 1. X equals 1 means I'm going to be knocking out this term here and this term here, leaving with this one here. So it's going to be b times 1 and 1 is 2, and 2 take away 1 is 1, and since it's just 1, that lot's just going to be 6 take away 7 take away 1, so that 2b equals negative 2, which means b equals negative 1. Well, that was fairly easy, not too much in the way of numerical calculations. What about another one? Well, I've also got negative 1, let x equal negative 1. And so if x is negative 1, I'll have this left, because that will cancel out and that will cancel out to 0, so they'll all go. So I'll have a times, now negative 1 is going to make that a negative 2, and negative 1 is going to make that a negative 3, and negative 1 is going to make that a 6, but plus a 7 minus a 1. So what I've got is 6a is going to be 12, which means a is going to be 2. Again, fairly straightforward and not too onerous numerically. But when it came to the last one, I'm going to have to do this. I'd have to say, let x equal a half. Now when x equals a half, they get knocked out and I'm left with this, but what am I left with? I've got c times 1½ times a half equals 6 times a half squared, which is 6 times a quarter, minus 7 halves minus 1, which, although it's only a piece of arithmetic, is still a bit annoying. So if it was a case like this, where even though you could use a simple numerical substitution just to knock out most of the arithmetic, you're probably just as well, when it gets to something a wee bitty nasty, to go to equating coefficients. So the one I've got left then is c. How can I find what c is? We'll just pick any of the terms. The simplest ones would be the constant at the end, because I've got these linear terms from quadratics, but I know straight away what the very last number is in each. So that if I just take the constant term, that'd probably have less arithmetic, because I'd have one lot of a, negative one lot of b, negative one lot of c equals negative 1. And I know what those are. So that c, if I take that over to this side and read it this way, is going to be 2, take away the negative 1, plus that one that's going to come over to join it, so c is going to equal 4. And that was probably easier numerically, even though the nature of that question suggested that I could just use straightforward numerical knockout values for the arithmetic. Right, a more complicated one. As a last example, what about this rational expression where you can see in the denominator there's only going to be one of the three parts that's going to have a knockout value. Right, so what would that be? Well, the first thing would be, with that replicated root, I'm going to have a over x plus 2 and then b over x plus 2 again, because there's two possibilities of terms that could divide into this. Plus, and that's irreducible, x squared plus 1, so I'll have to make that cx plus d. Right, there's 4 constants. Multiplying that all out, you would have, well, a still needs the other x plus 2 and that quadratic term. B just needs that quadratic term. And cx plus d needs that squared term, x plus 2 squared. And that lot should come to 5 minus 10x minus 14x squared minus 2x cubed. And then it's this case of what we do. Numerical substitutions, equating coefficients, numerical substitutions first of all anyway, because I've got a little linear term that can get knocked out. Unfortunately that one can't go. If it had been an x squared minus 1, I could have done something with it. Well here, so I've got what? So x equals negative 2 will do something. I'll knock out that one, I'll knock out that one, I'll leave me with this so I can get b straight away from that. So b is going to be negative 2 squared is 4 plus 1 is 5. I'll just put it in, it's 5. But see, the problem here with numerical substitutions is working out this expression here. So carefully going through that, I've got a 5, negative 10, negative 2 will be plus 20, negative 2 squared will be plus 4, so that'll still be negative, and that will be 56. Negative 2, that'll be negative 8, but that'll be plus 16. I've still got to be careful with arithmetic here. So I've got 36, so it'll be negative 20 minus negative 15. So finally I've got 5b is negative 15, so b is negative 3. Using numerical substitutions. Oops, a daisy. Now for the other ones, since there's nothing else that's going to knock them out, well, I'll carry on. The obvious step would be there's nothing else that's going to go, so I'll put in 0. Surely that should be easy. So putting in 0, what have I got? I've got a times, and then if that's 0, it's going to be a 2 times a 1. If that's 0, that's just going to be a b times a 1. If that's 0, that will just be a d. If that's 0, that's going to be a 2, but 2 squared will be a 4, and that lot will just come to 5. Now I know that b is negative 3, so what this reads is 2a plus 4d, and that's negative 3, bring it over, is going to be 8, or a plus 2d is going to be 4. So there's an equation. Next easier one is going to be x equals 1. So putting 1 into it all, I'm going to have a times, that will be 3, that will be 2, that will be 2, that will be c plus d, that will be 3 is 9, and that's going to be 5, take away 10, take away 14, take away 2. So that's going to give me 6a. The 2b is going to be a negative 6, I'll throw that over afterwards, plus 9c plus 9d equals, and then you have to be careful all of this, remember there's a negative 6 to go over as a plus 6, so that altogether I've got here negative 24, negative 26, that's negative 20, negative 20, so there's a negative 15 again, but everything divides by 3, so I've got 2a plus 3c plus 3d equals negative 5 for a second equation. Still not enough, because there are 3 unknowns, so I'd have to go for a third one, and I'm beginning to get fed up already because I know that now I'm going to have to go into negative ones, which just gets not that much trickier. So I'll use the same technique as before, equating coefficients. Get rid of this bit, just resorting to equating coefficients because of this horrible piece of arithmetic. Though there is one little drawback, I'd have to get these multiplied out, not necessarily, but just so I don't confuse my x's and x squareds and so on, how many there are in each. Although, to begin with, I wouldn't really need to because I can quite clearly see the x cubes and see the constants. Those are the 2 simple ones out of each of the products. But that wouldn't be enough because I've still got 3 to find, 3 constants in it, so I'll need 3 equations. So I'd have to get the x cubes, the constants, and then one of either the x squares or x's. So maybe it will just take time to multiply it out. So that lot's not too bad because that's just x cubed, 2x squared plus x plus 2. That doesn't change, x squared plus 1. It's still easier doing this arithmetic, doing this algebra than these wee bits of arithmetic, all the negatives and so on. Cx plus d times x squared plus 4x plus 4. There, that took no time at all. Equals this thing here. Right, the easiest ones are the outside ones. The x cubes and then the constants. Never mind all the gubbins in the middle. So for the x cubes, I'm just going to have an a, none there, and a c. So a plus c equals x cubes negative 2. Straight away, very quick. Constants. For the constants, I'm going to have a 2a, a 1b, c's won't exist at all. Oops, I'm doing it for should be here, and a 4d plus 4d should equal, and the constant equals 5. But I already know that b is negative 3, so I can simplify that. Take the negative 3 across and add, and I've got 2a plus 4d is 8, or knocking that down, a plus 2d equals 4. Now, there's my memory. I can't remember what I had before. I've forgotten already. So there's 2. Nice and easy. There's not been a lot of arithmetic doing that, but now I'll have to go for one of the other ones. So we'll just say x squareds. How many x squareds have I got? Maybe I should go in for x's, because look, there's no x's in that. And there's only a 1 there. I'll just go for x's. Right, go for the x's. So I've got an a, none from that term. I've got a 4c, and I've got a 4d. And those x's should come to negative 10. There's a third equation. So there's my 3 equations. And I think that's a bit easier than going through all the arithmetic to arrive still at the same thing of simultaneous equations. Then, it's a pity they're all different here, nothing to do, so it may be best to put those 2 together to make a's and c's. So if I want to knock out that, if I took 2 of 2 and left 3 alone, 2 of 2, 2a, 4d is 8. Leave this alone, a plus 4c plus 4d is negative 10. And then I'll do the top, bottom take away the top in this case. So I've got negative a plus 4c, and that disappears, and what was the bottom take away top, so that'll be negative 18. There's another equation, and then put that first one in beside it. That was number 1, which was a plus c is negative 2. Now I can add them. 5c is negative 20, so c is negative 4. And then it all just falls into place after that. Now the pins just start to tumble. C is negative 4. Well, that means a is going to be negative 2 plus 4, so a is going to be 2. And then for d, get that from here, now that a is 2, I've got that 2d is going to be 4 minus the 2, 2d is 2, so d equals 1. And then it's all done. All within one little bit of board, just by using a combination of numerical substitutions and equating coefficients. It's always easier, especially if there's lots of arithmetic to be done. So finishing off then, the whole thing would have been, well, what was that? A was, going cross-eyed here, didn't underline it, that's why, there it is. A is 2, so 2 over x plus 2. B is negative 3, minus 3 over x plus 2 squared, and over x squared plus 1, I had c, which was negative 4. Oh, there's a thing. Rather than writing negative 4x plus 1, I think I'll write negative of 4x minus 1, because subtracting the 4 or subtracting the negative 1 gives me the same coefficients. That would have been the answer, using a combination of numerical substitutions where convenient convenient only when it knocks out terms to reduce the arithmetic, and then resorting to equating coefficients and little bits of simultaneous equations. There we are.